Okay, so in the previous video, we watched, we looked at some examples of the midpoint rule and the trapezoidal rule applied to a specific integral, this guy right here. So the definite integral from 1 to 2 of 1 over x dx. And we found those approximations, and then we found the error in those approximations, how far off those were from the actual value of that definite integral. So next what I want to do is take a look at what would happen if we redid that, if we did more approximations of that integral, still using the trapezoidal rule and the midpoint rule, but also using the left and right endpoint methods, just so we have multiple things to compare for various different values of n. So we found the trapezoidal rule and the midpoint rule for n equals 5. In this table, we're also going to plug in n equals 10, n equals 20. We're not going to do that by hand because that's a lot of terms to write out, but it's easy enough to, program something that will output these values, either in Excel or something like that. This is straight out of your book. So if you notice, when n is equal to 5, our trapezoidal rule gives us this value, midpoint rule gives us this value. This is what we found when we did our own approximations in the previous video. But left endpoint and right endpoint, I can see that these are giving me worse approximations. Because again, remember, we know the exact value of this integral that we're trying to approximate the area, or just approximate the value of. And you can see that these values are further off from this than our trapezoidal rule and midpoint rule were. But something else we observed in the previous video is that the midpoint rule tends to give us about half the error once we take absolute values that the trapezoidal rule does. And what we want to see here is if n increases, do we see that trend still occurring? So coming down here, this table gives us the error terms for each of our approximations. And I can see when I compare the trapezoidal rule to the midpoint rule, if I were to take absolute values of all of these, then but I'm still seeing my midpoint rule giving me about half the error as my trapezoidal rule. So there's a few observations we want to make based on that to kind of guide where we're going with this. This is also straight out of your book. So the first thing is that when we increase n, the error terms get smaller, which means we're getting better and better approximations. And we expect this to happen. That's the whole reason why when you define the definite integral using those left and right endpoint methods in Calculus 1, that's why you take a limit as n goes to infinity, because we see that as n gets bigger and bigger, our approximations get better and better. So in the limiting case, we should get an exact answer. This is what we would have expected to happen. Another thing worth noting is that it says the errors in the left and right endpoint approximations are opposite in sign and appear to decrease by a factor of about 2 when we double the value of n. So that is referring to these error terms here. So what that's telling us is that the left endpoint method for this particular function is underestimating the area, while the right endpoint is overestimating. Sorry, I'm saying that backwards. This is overestimating the area. This is underestimating the area. Overestimating because if the area is too big, we'd have to add a negative error term to get down to the actual area, and vice versa here. So what it's saying is that as n doubles, these errors appear to be roughly getting cut in half each time. It's not exactly cut in half, but it's pretty close to that. Okay, so that's kind of indicating how exactly increasing n changes that error. The midpoint rule and the trapezoidal rules are pretty similar. And the third observation we already talked about, they are much better approximations than the left and right endpoint methods. Also, we noticed that the trapezoidal rule and the midpoint rules also appear to have opposite signs in their error terms. So negatives here, positives here. And they seem to decrease by a factor of about 4 when we double the value of n. So if you notice from this error term right here, 0.002488, if you divide that by 4, you're going to get a value pretty close to what we're seeing in the next term here. So 0.000624 with the negative out front. That means that as n increases, we are getting we are getting a much greater decrease in our error for the trapezoidal and midpoint rules than we're seeing in the left and right endpoint rules. These are only getting cut in half while these are being quartered. That suggests that these two methods are much more effective than the left and right endpoint methods. And then finally, which we did observe already, this fifth point here, the size of the error in the midpoint rule is about half the size of the error in the trapezoidal rule. Okay, so these observations are really helpful because they help guide us towards, you know, how to choose an approximation method when we're trying to approximate a definite integral. This next result here, we can't prove in this class. This is something you would prove in what's called a numerical analysis class, which is upper division or graduate level stuff. So we're going to use these results, but we can't show why they're true. I'm going to try and explain how they work, and then we'll see them in a couple of examples here. So again, when we're talking about these error bounds, we're integrating a function f of x over some interval a, b. So the f here is coming from the integrand, but it says suppose the absolute value of the second derivative of f of x is less than or equal to some constant k for this interval that we're integrating over. So that part's important. If your errors for your trapezoidal and midpoint rules are given by these values, then we can say that the absolute value of your trapezoidal rules error term is less than or equal to this quantity here. So k, it's this k that you're seeing right here that's appearing here, times b minus a, remember that would be the size of this interval, cubed over 12n squared. Notice that the error for the midpoint rule, after taking an absolute value, looks almost identical, except down here, instead of having a 12, we have a 24. That explains why the midpoint rule's error keeps coming out to roughly half of the trapezoidal rule's error, because this value here is exactly half of that value right there. Okay, and like I said, we can't prove at this level where these are coming from. So this is one of those few things that you kind of have to take on faith in this class. But I do want to see how these things sort of jive with the observations that we've made. So we did just talk about why this error is coming out to half of this one when we observe it in those tables on the previous page. But also this kind of explains why increasing n, the number of rectangles or trapezoids, gives us better and better approximations, because as n gets bigger and bigger, this denominator is getting bigger and bigger, which means this overall expression is actually getting smaller. So large values of n give us small values here, and this value represents an upper bound on that error term after taking an absolute value. So the error term has to be less than or equal to whatever this is. Okay, so if we can make this a small value, then we're getting ourselves small error terms, which means we're getting good approximations. So what I want to do first is I want to compute the error bound just for the trapezoidal rule when we used n equals 5 to approximate this definite integral. So we've already done this, but we want to use the error bound, this thing right here, to compute the absolute largest that the error on that approximation could have been. So let's do that here. To approximate this, I'm going to go up here, and I can see that this expression involves this k, which comes from this inequality right here. So the first thing I need to do is figure out what k is. I noticed that I need to find f double prime in order to figure that out. So we have f of x equals 1 over x, which means f prime is negative 1 over x squared, so that f double prime is equal to 2 over x cubed, okay? Now, absolute value of f double prime of x is going to be the same thing as the absolute value of 2 over x cubed. We just found that here. And the goal is to see what is the absolute largest that absolute value can be. We're finding a constant that acts as an upper bound for that. So Obviously, I can make this thing as big or as small as I want by just plugging in, whatever values of x I can dream up. But we're not allowed to plug in anything we want for x. We're restricted to this interval here, the interval from 1 to 2. So I know that if I want to make this thing as large as possible, small denominators give me large fractions. And on this interval, the smallest value I can get is that number 1 there. So this must be less than or equal to the absolute value of 2 over 1 cubed, which is just 2. So that thing right there is the k that's showing up here. Now, to compute that error bound, I say that the absolute value of e to the t has to be less than or equal to k, which here is 2, times b minus a. Remember, b is 2 and a is 1. Cubed over 12n squared. So here's where we factor in the number of rectangles or trapezoids that we're using. That's 5 squared. This is equal to 1 over 150, or approximately 0.00666. This goes on forever, so if we're rounding, we have a 7 there. Okay, so what this is saying is that this is the absolute most that our trapezoidal rule could have been off by. Now, if we look at the actual error, which we computed already in our trapezoidal rule over here, we had approximately 0.002, which is roughly a third of what that upper bound on our error is. So remember that this is the absolute largest that error can be. It doesn't mean that the error is going to come out to exactly that or even close to that. The error can be significantly smaller than what this error bound is showing us. It just cannot be bigger than that. Okay? All right, so this next example is asking us to use the trapezoidal and midpoint rules. We're not, well, let me back that up. We're not actually going to use them, but if we were going to use the trapezoidal and midpoint rules to approximate the area of this function, the area under this function over that interval from 1 to 2. So basically, we're approximating this definite integral. This is asking us to figure out how to choose n so that our approximation is within a specific error tolerance. We want to get this thing to be accurate within 1/10,000th, so 0.0001. The way that we do that is we use our approximation methods here. We don't know what n is, but we do know what we want our error tolerance to be. That's what's going to go here. So for example, for my trapezoidal rule, we know that we want the error to be no bigger than 0.0001. So that's what it means for it to be accurate within that amount. Okay, so in order to do that, we need that 0.0001 to be less than or equal to this guy. Remember, we already found what k was for this example. It was 2. So we have 2 times 2 minus 1 cubed over 12n squared. Remember, we don't know what n is this time. Okay, my goal here is going to be to solve for n. So one thing I can do is multiply both sides by 12n squared and then divide both sides by that 0.0001. That's going to give me 12n squared is less than or equal to, let's evaluate this too. 2 minus 1 cubed is just 1 times 2, which would be 2, over 0.0001. Let's divide both sides by 12 so that I get, this would become 1 over 6 times 0.0001. Okay, and then we know that n has to be a positive number, and so over the positive real numbers, the n squared function is increasing. And what that means is that if I take square roots of both sides, I don't have to flip that inequality sign. So I can write this as the square root of 1 over 0.0006 if I multiply that 6 in. This is where we'd enter things into a calculator. This is going to give me roughly 40.8. Okay, so n has to be less than or equal, or sorry, hold on, I think I got things flipped around here at one point. Hang on 1 second. I had this part flipped around. I just realized I did something I shouldn't have done. So backing this up, we actually want our error not to be, or we want n to not be less than this. We want it to be greater than this, because increasing n will give us better approximations for our error. So I need to flip this part around. Really, let me back things up here a little bit. What we wanted was this. We wanted this over 12n squared to be less than or equal to 0.0001. I had these two guys flipped around. So coming back, we know that the error has to be less than this, and if we make sure that this is less than or equal to 0.0001, then we would end up with all of the, we would have ended up with the correct error tolerance. So that was my mistake. So essentially what that's going to do is it's going to flip all of these around. I see where I went wrong there. Okay, so that's important because n has to be greater than or equal to 40.8. That's where I was looking at that and thinking that something's wrong there. N has to be a positive integer because it represents the number of trapezoids in this case. So for that reason, we can't just set n equal to 40.8. We have to go to the next largest whole number, which would be 41. So here I'm going to set n equal to 41. That's the number of trapezoids that we would need in the trapezoidal rule to get our approximation down to the desired level of accuracy. Okay, sorry about the little mistake there. If I were to do the same thing with the midpoint rule, we're going to have essentially the same set of steps, but if you notice, the only difference is that instead of a 12 there, I'm going to have a 24 there, because that was the only difference in our error bound. So for this guy, I'm going to do like this. We need 2 times 2 minus 1 cubed over 24 n squared to be less than or equal to 0.0001. Same idea, we're going to try and solve for n. So if I were to multiply both sides by this denominator, divide both sides by that, I'm going to get 2 over 0.0001 is less than or equal to 24 n squared. And then I'm going to divide both sides by 24, which would give me 1 over 12 times 0.0001. N squared is less than or equal to n squared. I'm going to flip things around. So that means n has to be greater than or equal to the square root of 1 over 12 times 0.0001. And this comes out to approximately 29. So again, oh, sorry, I was off the screen there. 29. That's coming from this after plugging it into a calculator. So if I need n to be greater than that, we can set n equal to, say, 30 to get our approximation within that desired level of accuracy. So you can see the benefit of the midpoint rule over the trapezoidal rule here is it takes less rectangles to get that level of accuracy than it does the number of trapezoids here. And the smaller we can make n, the less computation we have to do when we're doing our approximation method. That's ultimately one of the goals that we have, because it's really two things that we're after. When we're doing these approximation methods, we want a good approximation, but without having to do excessive computation. So if we're able to keep our error terms small while minimizing the amount of terms that we have to add up, that's going to kind of determine which approximation method is the best choice. Okay, we have more to talk about, but we're going to do that in the third part.